Okay. Let's do a parabolic hemisphere, whatever the heck that might be. So there's our general slicing method one more time. And let's look at this volume problem. So the volume of a parabolic hemisphere. Let's see if we can't make heads or tails of this. A solid has a base. A base. That's what we're looking for. We want to think about that base. By the curves y equals x squared and y equals 2 minus x squared in the xy plane. Okay. So x squared maybe looks like this. And we have y equals 2 minus x squared, so make that a 2. It would go down like that, except they'd have the same heights. They're both even functions. So that's the base right in here. This is the base of it. So we can see that we must have some values that we're going through, where they must hit. I'll let you know right now to save some time. That's from -1 to 1. Now, that's the two-dimensional. So what we're thinking is it's coming out of the screen at you. Coming out of the screen at you. Sorry, I can't draw. It's making some sphere, half a sphere. Let me get a picture for you, see if maybe this makes a little bit more sense. There we go. There it is. There's our two graphs. We got our x squared coming through right here, coming around the side. We have our 2 minus x squared coming around this way. There's our y-axis. Here's our x-axis. It's just kind of tilted for you. And then we're saying that there is some sort of semicircular slice that we're going to cut, and we're going to do this. Sorry, my drawing's probably not making it any better. But that's going to be our game, is we want to set that thing up. So we need to figure out what the radius. Now this one's already kind of doing the work for you. It's saying the radius of the slice. Because, wait a second. We need an area function. If it's a semicircular slice, do you know the area of a circle? The area of a circle is pi r squared. But we're doing a semicircular. That means half. So our area function is going to be 1/2 pi r squared. We have to figure out what that radius is. Because, of course, the radius is going to change depending upon where we're at. For this point here, the radius is probably at its biggest. At this point here, it gets a little bit smaller. As we keep moving in, the radius gets smaller and smaller and smaller and smaller. So the radius is just going to be half of whatever the distance is from our 2 minus x squared to our x squared. So back down here, it shows this, where it's saying here is our radius of the slice, which is going to be the difference between the top function and the bottom function. 1/2 of it, right? The difference in those heights. So our radius does become 1 minus x squared. Because we're just going to do that the radius is equal to 1/2 of the distance of the top one, 2 minus x squared, minus the one on the bottom, the x squared. We put this all together. We have 1/2, 2 minus 2x squared. So let's bring this in, and we find out our radius is 1 minus x squared. We're ready to go. I think we have this. Our area function with terms of x is going to be 1/2 pi something squared, and there it is. There's 1 minus x squared. So we had to know the area of a semicircle, plus we just needed to know the difference between these two heights, and then cut them in half for a radius. Well, now that we've done this, let's go get our volume. So our volume is from A to B of our area function dx. So our volume is going to be, remember we went from -1 to 1. And our area function is pi over 2, 1/2 pi, times 1 minus x squared dx. This must feel very familiar to y'all. I feel like we've done this problem before. All right, so now we're doing calculus. Let's first start by taking out that number. I don't want to deal with that. And, dude, I mean, I could cheat here. That's an even function. 1 minus x squared, that's freaking even. I could just multiply this thing by 2, and I think I'm going to do that. I just don't see any reason why. I don't want to plug in ones. I like zeros better. So since this is an even function, I'm going to pull a 2 out and call it 2 times pi over 2 and just go from 0 to 1 of 1 minus x squared. Let's just write it in. 1 minus x squared, 1 minus 2x squared plus x to the 4th. All right, isn't this an even function? Does that look even to you? That's even. It does the same thing on both sides of the y-axis. Okay, going back, sorry, getting all excited. So our volume is equal to pi times our integral. So let's do our integral. It's going to be the same thing we had from before. It's kind of convenient. So since we have already done this in our last one, we put all this together and we find out that this is just going to be, what, 8 over 15? Sorry, we've already done this problem. I don't want to put all the numbers back in there. And we get a volume of 8 pi over 15 units cubed. So how you like this section so far? If you're a visual learner, this should be better for you because you can actually see it, touch it, mess with it, kind of think about it. If you're more process driven like myself, this could be a real big challenge. I know students typically tend to struggle with this. It might be because I'm a terrible teacher at this, but I don't know. It's not the simplest stuff. I know I struggled with it when I was a student, but you aren't going to get too bad with it. I typically like to do the disc and washer method rather than doing just shapes like this on exams. So that might be some good news. But throughout your homework, you need to be able to deal with them. So, all right, in the next one, we're going to get more into what I think to be test-level problems, the sorts of ideas we're going to have. Yeah, more pictures from the book. And again, I'm going to keep sticking with the examples from your textbook. So if anything's not making sense and you want to go and double-check it, all this stuff is in your textbook. You can just find it in the e-text. So, all right, on to the next.